This video is going to take a look at the standard normal distribution and then also the normal distribution in regards to z-scores and standard deviations. A standard normal distribution is a bell curve and it has a mean in the middle of 0. In real life, it's really difficult to find a situation where your mean is actually 0. And then one standard deviation above the mean and one standard deviation below the mean is where 68% of the data should fall. And then between the second standard deviation below the mean and above the mean, there's 95% of the data. So that's the blue, tan, and then blue added together. And 99.7% of the data is between 3 standard deviations below the mean and 3 standard deviations above the mean. And like I said, the mean is 0, and the standard deviation has to be 1. So this is such a unique situation where the mean is exactly 0 and the standard deviation is 1, that this standard normal distribution curve wouldn't be useful for most anything in statistics unless we could adapt it. And that's what a z-score allows us to do. A z-score allows us to take the standard normal distribution and utilize it with any normal distribution. So first we need to know what a z-score is. Well, a z-score formula is that you take x, and x is a data value. So you take a data value, you subtract the mean of that particular population, and you divide it by the standard deviation. So let's go over what this is actually doing. This x minus the mean is finding the difference between a data value and a mean. And then it's dividing it by the standard deviation to scale it in such a way that the standard deviation can be considered to be 1. I found this graphic and really liked it. It helps us see that a z-score converts data from normal distributions to standard deviations in the standard normal distribution. So what happens is we get a data value, say 990, and we're able to utilize that formula along with the mean and the standard deviation to then figure out that that 990 is actually a -1 standard deviation in the standard normal curve. And I could do that for any data value. The chart in green has these numbers on here so nicely that it makes it look like every single data set is just going to be picture perfect. Well, that's not the reality. Not every data distribution is perfect, but most of them are near a normal distribution. And when you're near a normal distribution, you can figure out what data value in your data set is actually 1 standard deviation below that mean, or 2 standard deviations below, or 3 standard deviations below, or likewise with above. So we take this normal distribution, we subtract the mean, and we divide by the standard deviation to create values that are actually in the standard normal. I wanted to take, for example, the intelligence scale, the IQ scale. An IQ scale has a mean of 100 and a standard deviation of 15. That's really nice. So what that tells me is that right here in the middle, this is your mean. It's 100. And if I were to subtract 15 from that, I would get 85. And that's 1 standard deviation below the mean. So in the standard normal curve, the mean would have been 0 because it's 0 standard deviations away from the mean. And the 85 would be -1 or have a z-score of -1. If I go back to that 85 and subtract another 15, because that's the standard deviation, I have 70. And that's 2 standard deviations below the mean, or in the standard normal curve, a -2. So a z-score of -2 would connect to the 70. Let's go above the mean for a moment. If I were to add 15 onto 100, I would have 115. That's one positive standard deviation above the mean, so my z-score is 1. If I add another 15, I have 130. So I am 2 standard deviations above the mean, and my z-score would be 2. I'm going to go and use that formula to verify what we know this next one should be. If I have a data value of 145, and I subtract the mean from it, divide by the standard deviation of 15, I find out that my z-score is 3, which is exactly what we knew it should be. It should be a 3 because it's 3 standard deviations above the mean.